morning students, welcome to the chemistry class. So in the last session we were discussed about the atomic models, in that both J.J. Thomson model as well as Rutherford atomic model were failed, and Rutherford atomic model was disproved by Maxwell. Okay, Maxwell disproved Rutherford atomic model. So according to Maxwell, the nucleus, all positive charges are concentrated if it is concentrated at the center, and the electron, if it is rotating around the nucleus, then electron being a charged particles, it get accelerated. Electron is get accelerated. When a charged particle under acceleration, it emits energy. It loses its energy in the form of radiation. Okay, when electron under revolution, if it loses energy, it due to centripetal force, okay, it is fall into the nucleus. This is the centripetal force. Due to centripetal force, it has to come near to the nucleus and fall into the nucleus, and thereby the atom will collapse. Okay, but still atom is stable. So Rutherford couldn't able to explain the stability of an atom. Centripetal force, the force acting towards the center is called centripetal force, and the force acting away from the center is called centrifugal force. Here the centrifugal force is Coulombic force of attraction, and centripetal force, this is so that it is attracting towards center, and so that because it loses energy in the form of by emitting in the form of radiation, by emitting the energy in the form of radiation, it will fall into the nucleus. According to Maxwell, any charged particle, okay, it will emit energy, it will loses energy in the form of waves, those are called radiations. These waves are called radiations. Okay, in the same time Maxwell, then de Broglie, then Planck's and Einstein, like this number of scientists, they were working on light. They were studying the properties of light as well as the atomic models and the properties of electron, proton, neutron. And all the scientists, they were got different results in different experiments, but all they were shown that theoretically as well as practically the results were true. Okay, and finally all they concluded that the light shows the behavior of wave property as well as particle property. Okay, so they concluded that, all the scientists, they concluded that the light behaves in some of the experiment, it behaves as a wave, and also this behaves as a particle. Okay, so that is called dual nature of matter. Okay, so here for example, in few properties like reflection, refraction, interference and diffraction, in these cases the light acting as a wave, in some other experiments like photoelectric effect, black body radiation, collision, in such cases this light acting as a particle. Okay, so in a few cases it was behaved as a wave, and in other cases it was acting as a particle. Okay, so now I will go one by one. First I will start with the wave. So let us study the properties of wave. It is motion of energy from one point to another point without transfer of matter. Okay, motion of energy from one point to another point without transfer of matter is called wave. Okay, so here from here this point to there is a transfer of energy to another point. Only energy it is going to transfer. Only energy it will get transfer, not the matter. Matter will not get transfer from one point to another point. Only energy it will transfer from one point to another point. Okay, so next the matter the wave we are going to represent graphically like this, and this is the origin point O, and here the positive coordinate and these are negative coordinate. Okay, so like this we are going to represent wave. This is called crust. Positive coordinate is called crust and negative coordinate is called trough, and this is one complete wave. Okay, similarly this is one complete wave, one crust and one trough. The wave associate with one crust and one trough. Okay, then here the distance between two consecutive crust and two consecutive crust or the two consecutive trough is called wavelength. That one symbol lambda. So first one is important terms in wave is wavelength. Okay, so the symbol is lambda. That is the wavelength is the distance between two consecutive crust or the distance between two consecutive trough is called wavelength. So this is the distance. So the SI unit are so, and also this wavelength it may be from very small distance to very large distance, different for that depends on different radiations, and so that we are using centimeter, meter, Armstrong unit, nanometer, picometer. Okay, so like this different units we are mentioning. We know that Armstrong unit, 1 Armstrong unit is equal to 10 to the power of minus 10 meter, and 1 nanometer, that is 1 nanometer is equal to 10 to the power of minus 9 meters, and 1 picometer is equal to 1 picometer 10 to the power of minus 12 meter. Okay, so like this from centimeter, meter to picometer, very small distance. Okay, so like this we are using wavelength. Next important term is frequency. The symbol is nu. So this frequency, so here the number of waves pass through a point per second is called frequency. The number of cycles per second is called frequency, or the number of waves pass through a point per second, in per second, 1 second is called frequency. Okay, it's frequency. So this is per second or hertz. In hertz also we are mentioning this frequency. These are the unit, SI unit for frequency. Okay, the number of cycles per second or the number of waves passed through a point in 1 second is called frequency. Okay, so next to velocity. This symbol is c. The distance traveled by wave in 1 second is called velocity. Okay, distance per unit time is called velocity. The symbol is c. Okay, and for a particular wave with the wavelength lambda and frequency nu, c is given by nu lambda. C is given by nu into lambda. Okay, so next to time period. The symbol is capital T. This is the time taken by the wave to pass through a point, to the time taken by one wave to pass through a point is called time period. Okay, the time taken by the wave to pass through a point is called time period. So it is T is given by 1 by nu. T is given by 1 by nu. Okay, so this is seconds per cycle. So for frequency, this is per second. So reciprocal of frequency, seconds per cycle. Unit is seconds per cycle. Okay, next to wave number. The symbol is nu bar. Wave number symbol is nu bar. This is reciprocal of wavelength. Wave number is reciprocal of wavelength, or nu bar is equal to 1 by lambda, or the number of waves in 1 meter. The number of waves in 1 meter is called wave number. The number of waves in 1 meter is called wave number. The SI unit is per meter. SI unit is per meter. Okay. The height of the crest or the depth of the trough is called an amplitude. The symbol is A, and it is going to determine the brightness of a beam of light. The amplitude square is given by an intensity. I is equal to A square. So these are the important terms to represent a wave. According to Maxwell, any charged particle under acceleration emit energy in the form of wave. That wave is called as radiation. Okay, any charged particle under acceleration, when it rotates, okay, it emits energy in the form of wave. That wave he called as radiation. Okay, and these radiations can travel in space. They not required medium. Medium is not required. No medium. Even without medium also they can travel from one point to another point. And next point, these radiations are always associated with electric field. And also they are also associated with magnetic field. They are associated with electric field and magnetic field. Okay, next, all these electric field and magnetic field are perpendicular to the direction of propagation, so that all are perpendicular to each other. Suppose this is the direction of propagation. Then this is perpendicular to the direction of propagation. There is an electric field. Okay, and perpendicular to both electric field and direction of propagation, there is a magnetic field. So that to the direction of propagation, electric field is perpendicular to direction of motion. To the direction of propagation, electric field is perpendicular, and both electric and perpendicular to the direction, magnetic field is perpendicular. Okay, and so thereby all electric field, magnetic field and direction of propagation are perpendicular to each other. Okay, and then here these electromagnetic radiation always they travel in space with velocity 3 into 10 to the power of 8 meter per second. They travel in space with velocity 3 into 10 to the power of meter per second. That is C. That is a constant. Okay. All the radiations Okay, in space they travel with velocity 3 into 10 to the power of 8 meter per second, irrespective of nu and lambda. Nu and lambda, whatever may be the nu, okay, or lambda, all radiations are travel with velocity 3 into 10 power of 8, and so that nu is equal to c by lambda. That c is a constant, velocity constant, that is velocity of light. Okay, so c is equal to nu lambda. C is equal to nu lambda. C is a constant. It is the product of frequency and lambda of particular radiation. Okay, so if you go on arrange a different a series of electromagnetic radiation in increasing order of their wavelength or frequency, then we are going to get a series. That series is called spectrum, electromagnetic spectrum. Electromagnetic spectrum. That series of electromagnetic radiations is called electromagnetic spectrum. Here this is a continuous spectrum. Here there is no gap. Okay, one by one all type of number of frequency radiations we will get it. That series is called electromagnetic spectrum. So this electromagnetic spectrum, in electromagnetic spectrum means the collection of dispersed light. The collection of dispersed light giving its composition of wavelength. Giving its composition of wavelength is called spectrum. You take a prism. Through prism, you allow the radiation to white light radiation to pass through that prism. It is going to disperse. It is going to disperse 7 different colors. So this is, it is going to form a band of wavelength. Okay, it is containing all radiations, all different radiations. Okay, so this is called spectrum. Okay, so here we are observing it is a collection of dispersed light, giving composition of wavelength, different wavelengths. Each line represents each wavelength. Okay, so this is spectrum. So in spectrum we have two types, emission spectrum and absorption spectrum. Okay, so first I will take absorption spectrum. You take a candle, and this emit all type of radiation. This candle, it is going to emit all type of radiation, and you allow this radiation to pass through a sample which containing KCl. Pass through a container which containing KCl. So then in this band, so this is a bright band, so it is going to absorb a particular radiation. This sample, this is the characteristic property of each matter. Each matter, they are going to absorb a particular radiation, and thereby it is going to form a dark space. This shows that absence of a particular radiation. This is called absorption spectrum. Remaining radiations, it is appears in a bright form, bright space. Okay, bright space. So this also bright. In that bright spectrum, bright space, only one dark line it is appears. Dark space is, it appears a particular single wavelength it is going to miss from this band. So that is called absorption spectrum. That is a particular, all the matters, a particular matter, it is going to absorb a particular radiation. That absence of radiation, it appears in the form of dark band. So that is called absorption spectrum. Okay, then I will come to emission spectrum. Okay, so here you take an example of so this in emission spectrum we have two types, continuous spectrum and line or atomic spectrum. In continuous spectrum you take an example of bulb or a sun. Okay, so which is going to emit all type of radiation, So here you see you are going to get a spectra like this, so which is containing all type of radiations, all type of frequency radiation or wavelength radiation, like this you will get it. This is continuous, there is no gap here. If you take VIBGYOR, so that is also continuous spectrum, This is like this. There is no gap. There is no gap. Okay. So without gap, it is going to form band of wavelengths. So this is continuous emission spectrum. So this is emitted by some array sources. Okay. They are going to emit all type of radiations. Then you take another example. So take a candle, take any source, and you heat, you allow these radiations to fall on NaCl. Okay. So or heat it NaCl. Then they are going to absorb this energy, and they will go to excited state. After absorbing energy, the electrons in the particular substance, it is get excited to higher energy. This is called ground state. Okay. So then this is unstable. Excited in a state, always it is unstable, so that it will come back to ground state. And this going to emit absorbed radiation. It is going to emit the absorbed radiation in the form of radiation, and thereby there is a formation or appearance of a bright band, a bright line. So this is bright line. So this is called line spectra. Only one single bright line we are observing here, in absence of all other wavelengths, okay. We are keeping filter, only it absorbs only particular radiation. Then after that I will stop it. We are allowing a particular radiation to fall on this. It is going to absorb a particular radiation. After absorbing, it will get excited to higher energy, and that higher energy is unstable. Excited state is unstable. Then it will come back to ground state by emitting absorbed radiation. Then that appears in a bright line. So this is called emission line spectrum, or atomic emission line spectrum, atomic spectrum. Okay. So this is bright in nature. This is absence of light. Okay, empty space are there, absence of light. Okay, so this is called line spectrum or atomic spectrum. Okay, so clear? A series of electromagnetic radiations is called electromagnetic spectrum. All these radiations, gamma rays, X-rays, UV, visible, IR, microwave, and radio waves. All these, they travels in the space. They not required any medium. Okay, even they are travels in space. Okay, and these radiations are associated with electric and magnetic field, and so that these are called electromagnetic radiation. Okay, so here while writing the spectrum, so here one note for you. First you write this box you write, and while writing the frequency, to make it easy, you mark it 10 to the power of 0 to 2 mark. Okay, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 10 powers you write, and simultaneously below that you start from 8, decreasing order. This is increasing order, and here it is decreasing order. 10 to the power of 8, 10 to the power of 6, 4, 2, 0, minus 2, minus 4, minus 6, minus 8, minus 10, minus 12, 14, minus 14, and minus 16. Okay, like this you write, and you make a table. Okay, here approximately around frequency, I am telling with respect to the frequency, approximately around 10 to the power of 8, 10 to the power of 8, 10 to the power of 6. Okay, around 10 to the power of 8 radio waves it will starts from onwards. From 10 to the power of 8 to 0, it is longer radio waves. Under that, FM, frequency modulation, amplitude modulation, this is around 10 to the power of 8. Around 10 to the power of 8 frequency we are getting frequency modulation, FM radio, and AM around 10 to the power of plus 6 frequency. Okay, in that frequency we are getting AM. Then remaining longer radio waves. Then microwaves around 10 to the power of 10. 10 to the power of 10. Okay, so this is microwaves, and IR between 15 to 11. IR radiation around 10 to the power of 15 hertz. 15 hertz we are getting visible radiation. These visible radiations, so this is VIBGYR. These visible radiations, that is VIBGYR. Okay, this will appear around 10 to the power of 15 hertz. Okay, and here this is red light, violet, indigo, blue, green, yellow, orange, red. Okay, this red having longer wavelength among VIBGYR, invisible light. Red having longer wavelength, violet having shorter wavelength, but red having less frequency, violet having larger frequency, higher frequency radiation. Okay, energy is more for violet radiations, energy is less for red radiations. Okay, and these red radiations having longer wavelength, and so that during sunset and sunrise the sky appears red, because it can travel for a longer distance, and it is less bends. It won't bends with a longer angle, okay, large angle, and so that during sunset and sunrise the sky appears red because of longer wavelength of red radiation in visible radiations. Okay, so violet bends larger, red color bends lesser. Okay, so here and VIBGYR, the green color is at the center. You have to keep in mind, that is for competitive exam they will ask this one. Okay, so next UV radiation around 10 to the power of 16 UV radiations. Then X-rays from 19 to 17 around 10 to the power of 18 X-rays we will get. These are hertz, this is frequency, and from 19 onwards gamma rays. Okay, so here these radio waves we are using in broadcasting. Okay, broadcasting we are using radio waves, and this one microwaves we are using in radars we are using microwaves. IR we are using for heating purpose we are using heating. And visible light, we know that without visible light there is no life on the earth. Okay, these are must, this visible radiation is must for photosynthesis. For photosynthesis it is must. Without photosynthesis there is no life and there is no production of food, and so that it is must for photosynthesis for the survival of all living beings on the earth. Okay, and also our eyes detect only this frequency radiation around 10 to the power of 15 hertz frequency our eye can detect. Okay, but for remaining radiations we need an instrument. These are not detected by our eyes. Okay, our eyes are not able to detect these radiations, we need an instrument. But the around 10 to the power of 15 hertz frequency radiations can detected by our eyes, and so that when it falls on the other substance, so that substance also appears, so we can see the different matter on the earth, and also we can identify this radiation. Okay, so this visible radiation, that is in VIBGYR, it will start around 400 nanometer to 750 nanometer. This is wavelength. Okay, so this is wavelength. Okay, wavelength increases from violet to red radiation. Violet around 400 nanometer we will get, and red color we will get around 750 nanometer. Okay, so wavelength increases from violet to red color, and that will starts from 400 nanometer to 750 nanometer. Nanometer in the sense 400 into 10 to the power of -9 meters. Okay, in meters if you want to convert, 400 into 10 to the power of -9 meter. So in this range we are observing visible radiation. Next to UV radiation, that is the part of sun rays. Okay, UV radiation, and X-rays we know that these X-rays, UV radiation, X-rays and gamma rays are high frequency radiations. this one when exposed to UV radiation too much, then there is a leads to cancer. Okay, and X-rays we are using in medicinal field. X-rays and gamma rays we are using in medicinal field. We are well known that one. These can penetrate through our muscle but not through bones, and so that they are going to form image. And the gamma rays and remaining high frequency radiations we are using for cancer treatment also. Okay, so this is about electromagnetic spectrum. The here spectrum, you see there is a continuous frequency radiations we are observing. This is a band, there is no gap. All radiations having a particular frequency and a particular wavelength. We are defining radiation using mainly frequency and wavelength. Okay, all these radiations travel in space with velocity c and is given by 3 into 10 to the power of 8. Okay, and also here nu is inversely proportional to 1 by lambda. If frequency increases, lambda value decreases. Lambda increases, frequency value decreases, and so that nu frequency is inversely proportional to wavelength, or nu is equal to c by lambda, where c is a constant. That constant, that is the velocity of light in space, that is 3 into 10 to the power of 8 meter per second. Okay, or c is equal to nu lambda. Okay, so with all these velocity of light, all the radiation is constant. All these radiation, they travel with velocity 3 into 10 to the power of 8 meter per second. Even though there is a difference in their frequency and wavelength, but they used to travel with a constant velocity, that is 3 into 10 to the power of 8 meter per second. Okay, and so that c is constant, it is always the product of frequency and wavelength. C is equal to nu lambda, or nu is equal to c by lambda. Okay, because nu is inversely proportional to 1 by lambda, or lambda is inversely proportional to 1 by nu. Okay, so this is about electromagnetic spectrum. Okay, the phenomenon like interference and diffraction, these were able to explain based on the wave properties of electromagnetic radiation. The phenomenon like black body radiation, photoelectric effect, and heat capacity of solid as a function of temperature, and the line spectrum of hydrogen. In this experiment, the results were couldn't able to explain based on the wave properties of electromagnetic radiation. So black body, in the sense, it is an ideal body which emits all the radiation and which absorbs all the radiation, are called black body. Okay, in a black body, you take an iron and you go on heating that one. In the beginning it will becomes light red, then if you go on increasing the temperature, it becomes very red, then blood red. Okay, it becomes dark red, then finally it will becomes white, then finally once again it will becomes blue. If you go on heating the iron, the color of the iron also changes. Okay, so if you draw that variations with temperature, if you draw in graphically, so at lower temperature, so we will get a graph like this with so it goes on increasing the energy. Okay, then it is going to reach a maximum at a particular wavelength. Okay, so this is the maximum. Then it will stop here. Then it is starts radiating. It emits energy in the form of radiation, and then it emits radiation. Okay, at a low temperature, low frequency. Okay, it is going to emit radiation, low frequency. Then you go on increasing the temperature. So here also it goes on increasing the temperature, it is absorbing the temperature still, then later it is going to reach the maximum, then later it is emitting radiation. But here you see here in this temperature, at T1 temperature, this is the maxima. So this is the maxima, and here this is the maxima. So here with respect to this maxima, the wavelength is around 1000 1500, and with respect to this the wavelength is around 1000. Okay, with increase in temperature the substance emits, so this the substance emits low wavelength radiation, high frequency radiation. With the temperature increases, they are going to emit radiations with the higher frequency, or the maxima shifting towards lower wavelength. If you go on increasing the temperature, the maxima shifting towards lower wavelength. It means that they are going to, if you increase the temperature, they are going to absorb higher energy radiation, and they absorb higher energy, they emit higher energy frequency. Okay, in case of iron, in the low temperature it will becomes red, it will absorb red radiation and emit red radiations. Then when it is become at higher temperature, it becomes blue and it emits blue radiation, which are low wavelength, higher frequency. Okay, so here these experimental results couldn't able to explain based on wave property of electromagnetic radiation. So that for that Planck suggested any atom or a molecule, it is going to absorb or emit radiation in a discrete form. Discrete form, not continuously. Discrete energy quantities. Discrete form, in discrete quantities. Okay, that discrete quantities he called them as quantum. And energy of each quantum is given by E is equal to h nu. He given the energy of each quantum is E is equal to h nu, where h is equal to, he given the value, he calculated and he given the value 6.626 into 10 to the power of minus 34 joule second. Okay, and h he called as Planck's constant. Planck's constant. Okay, so h is equal to 6.26 into 10 to the power of minus 34 joule second. This is the constant value given by Planck. Okay, based on this theory, he was able to explain the results of black body radiation. Okay, and for n number of photons, he has given nh nu. For n moles he has given E is equal to nh nu. N is number of moles. For n value he has given E is equal to nh nu. Okay, so next in 1887 Hertz performed an interesting experiment, that is photoelectric effect. Okay, so according to Planck, for quantum he called as photons. Okay, when photons that is light radiations falls on metal surface, these are an electrons. Okay, these are an electrons with energy h nu, falls on the metal surface with energy h nu, then they are going to eject an electron from the metal surface. That phenomenon is called photoelectric effect. The ejection of an electron from the metal surface when light radiation incident on the metal surface is called photoelectric effect. Okay, so there is an ejection of an electron when light radiation falls on the metal surface. They allow the radiation with frequency with energy h nu, then there is an ejection of an electron. Okay, for that he constructed one experiment. So here they kept metal plate and they connected that one to battery. Through ammeter he connected to detector. They kept detector to identify the ejection of an electron from the metal surface. They allowed the radiation to incident on the metal surface. As soon as the radiation incident on the radiations in the light with energy h nu incident on the metal surface, there is an ejection of an electron, and thereby they will pass through the detector and pass through the circuit. There is a flow of current, and that will shown by ammeter readings. Okay, this deflects. That deflects indicates there is a flow of current in the metal surface. Okay, so photons means for quantum he called Planck's called as photons. Okay, when photons incident on the metal surface, there is an ejection of an electron, and thereby there is a flow of current in the circuit. So that is photoelectric current. That the current is called photoelectric current. That effect is called photoelectric effect. In this experiment, they observed first one, as soon as the light radiation incident on the metal surface, there is an ejection, immediately there is an ejection of an electron. There is no time lag between incident radiation and ejected electron. Immediately when it incident, immediately there is an ejection. When the light radiation incident on the metal surface, there is an ejection of an electron. So there is no time lag. They will not take time. So now if it incident on the metal surface, tomorrow there is no. Tomorrow immediately there is an ejection of an electron. There is no ejection of an electron tomorrow. Okay. Then immediately there is an ejection of an electron. That is called no time lag between incident radiation and ejected electron. And the second point, the incident radiation should have minimum frequency. Below that there is no ejection of an electron or there is no photoelectric effect. Okay, there should be a minimum frequency for each metal. There should be a minimum frequency radiation we have to incident on the metal surface. Below that there is no ejection of an electron. That frequency he called as threshold frequency. Threshold frequency, that is nu naught. It means we have if it requires 100 frequency radiation, okay, then just imagine that there is a photoelectric effect. If we allow the radiation with frequency 80 hertz, there is no ejection of an electron. Just it will shines. There is a bright spot on that we are observing, just it will vibrate. Okay, there is no, it will not come out from the metal surface. It will retain, just it will vibrate, so that it will shines. Suppose if I add 200 hertz incident radiation, suppose if I allow radiation with the frequency 200 hertz, then it will eject an electron, and electron will move with some velocity, or it is associated with kinetic energy equivalent to remaining 100 hertz. Remaining 100 hertz, it will appear in the form of kinetic energy. Okay, so if we allow the radiation with frequency more than threshold frequency, that frequency appears in the form of kinetic energy. Along with electron. Okay, so that this minimum frequency it is required to incident on the metal surface. That frequency, this threshold frequency, depends on nature of metal. For generally we are using here. This is potassium or cesium or rubidium. Generally we are using cesium more, and because it is more electropositive element in the periodic table, and so that we are using cesium metal in solar system. In photoelectric effect experiment we are using cesium. Potassium, first group has black element, potassium, rubidium and cesium we are using here. These have low ionization energy. As soon as the incident radiation falls on the metal surface, there is an ejection of an electron immediately. Okay, so there should be a minimum frequency. That frequency is called as threshold frequency. Then third one, the number of electrons ejected. The number of electron depends on, directly proportional to intensity of radiation. Intensity of intensity of incident radiation. If I allow, that means brightness. So if I allow 2 radiations with threshold frequency, then there is a emission of 2 electrons. If I allow 100 radiation, then there is ejection of 100 electrons. So that number of electrons ejected depends on intensity or brightness of incident radiation. Okay, so here h nu, it is the incident radiation, and here so it requires for ejection of an electron h nu naught. Okay, so minimum energy it is required. This is called work function. H nu naught is called work function. Work function for ejection of an electron from the metal surface. Okay, now the remaining difference in energy, it appears in the form of kinetic energy. That kinetic energy is equal to of mv square, MeV square. That is, Me is the mass of an electron, V is the velocity associated with ejected electron, photoelectron. So now h nu is equal to h nu naught plus of MeV square. Okay, or h nu minus h nu naught is equal to kinetic energy, that is of MeV square. Okay, so the difference in energies, difference in incident energy and the work function, it will give you the kinetic energy of ejected photoelectron. This is called photoelectron because photo means incident. This is contained in quantums, that photons when incident on the metal surface, that is ejection of an electron, that electron is called photoelectron, and that electricity is called electricity passed through the circuit, and that effect is called photoelectric effect. Okay, here in this experiment, this experiment also we can't able to explain based on wave property of electromagnetic radiations. So to eject an electron from the metal surface, the light should have particle nature. Only when a particle is so when, if you just consider this is a particle, then another particle when hit on the metal surface, then only an ejection of an electron should occur. When light, electromagnetic radiation, that light when it is acting as a particle nature or exhibit particle nature, then only ejection of an electron we can expect here, not like a wave particle. Okay, so this experiment clearly shows that the electromagnetic radiations exhibit particle nature also. So we can, their displacement will occurs only when the particle hits on this electron, then there is a displacement of an electron, it will occurs. Okay, so otherwise if it is a wave property, it can't able to eject an electron. Okay, so it should be a particle property, then only we can expect ejection of an electron from the metal surface. This experiment clearly shows that these electromagnetic radiations exhibit particle nature. Phenomenon like interfaces diffraction can able to explain based on wave property of electromagnetic radiation. Then the experiments block body radiation and photoelectric effect. These phenomenon clearly says that electromagnetic radiations exhibit particle nature. So finally scientists concluded that when radiation interacts with matter, then they are acting as a particle, they exhibit particle nature. When it propagates, it behaves or exhibit wave nature. Okay, that is called dual nature of electron. It exhibits both particle nature as well as wave nature. That is called dual nature of electromagnetic radiation. Then these radiations are a stream of particles. These radiations are having a stream of particles. Then that stream in that packet of energy, they are called as photons with energy h nu. Okay, then that is dual nature of electromagnetic radiation. Light behaves both as particle as well as wave. Okay, so that is dual nature of electromagnetic radiation.